Imagine a computer so powerful that it makes even the most advanced supercomputers look like toys. A machine that can solve complex problems in seconds, problems that would take classical computers millions of years to crack. This isn't science fiction, it's the promise of quantum computing, a revolutionary technology that could change the world as we know it. But what is it, and how does it differ from the classical computers we use every day? Let's dive into the fascinating world of quantum mechanics to find out. Classical computers, like the one you're using to read this, store information in bits, which can be either a 0 or a 1. This binary system is the foundation of all classical computing. It's like a light switch that's either on or off. Simple yet effective for many tasks. Quantum computers, on the other hand, use qubits. These are not just any ordinary bits. These qubits are strange beasts that can be 0, 1, or both at the same time. This phenomenon is known as superposition. This mind-bending ability stems from the principles of quantum mechanics, a branch of physics that governs the microscopic world. It's a realm where the rules of classical physics no longer apply. It's a world where particles can be in multiple states at once, where uncertainty is the norm, and where things behave in ways that defy our everyday intuition. This is the essence of quantum mechanics. Quantum computing harnesses these bizarre quantum phenomena to perform calculations in ways that are simply impossible for classical computers. It opens up new possibilities for solving problems that were once thought unsolvable. It's like having a computer that can explore every possible solution to a problem simultaneously, making it exponentially faster for certain tasks. The potential applications are vast, from cryptography to drug discovery and beyond. Let's delve deeper into the heart of quantum computers' qubits. These are the fundamental building blocks that make quantum computing so powerful and unique. Imagine a coin spinning in the air, not yet landed on heads or tails. This spinning coin is a great analogy for understanding qubits. That's a qubit. It exists in a state of superposition, a mix of both possibilities until we measure it. This superposition is what allows qubits to perform complex calculations. In the quantum world, particles like electrons or photons can act as qubits. These tiny particles are manipulated to represent data. Their properties, such as spin or polarization, represent the 0 and 1 states. This is similar to how classical bits represent data, but with a quantum twist. But unlike classical bits, qubits can be in a combination of both states simultaneously, thanks to superposition. This duality is what sets qubits apart. Think of it like a musical chord. A chord is richer and more complex than a single note. A single note played on a piano represents a bit, either a C or a D, for example. It's simple and straightforward, but a chord combines multiple notes, creating a richer, more complex sound. This is akin to how qubits work. Similarly, a qubit can be a blend of 0 and 1, holding much more information than a single bit. This blend allows for more sophisticated data processing. This ability to exist in multiple states at once is what gives quantum computers their incredible power. They can solve problems that are currently impossible for classical computers. It's like having a computer that can explore every possible path in a maze simultaneously, finding the solution much faster than a classical computer that has to try each path one by one. This parallelism is the key to quantum computing's potential. Superposition is a mind-bending concept, but it's key to understanding the power of quantum computing. In the classical world, things are either one way or another, but in the quantum realm, they can be both at the same time. It's like a spinning coin that's both heads and tails at the same time until we force it to collapse into one state by observing it. This duality is what makes quantum computing so revolutionary. This inherent uncertainty is not a flaw but a feature of the quantum world. It allows for a new kind of computation that can solve problems in ways we never thought possible. It allows qubits to explore a vast space of possibilities simultaneously, making them incredibly efficient for certain types of calculations. Imagine searching for a specific grain of sand on a beach. A classical computer would have to examine each grain one by one, a painstakingly slow process. A quantum computer using superposition could analyze all the grains at once. This parallel processing capability is what sets quantum computers apart. This ability to explore multiple possibilities simultaneously makes quantum computers incredibly powerful for certain tasks, such as optimization and cryptography. For example, they could revolutionize drug discovery by simulating complex molecules and their interactions, which is currently a very time-consuming process. Speeding up the development of new medicines and potentially saving countless lives. Of course, harnessing the power of superposition is a delicate dance. Qubits are extremely fragile and maintaining their state is a significant challenge. Any disturbance, even a tiny vibration or change in temperature, can cause them to lose their quantum properties, a process called decoherence. This is one of the biggest hurdles in making practical quantum computers. If superposition is strange, then entanglement takes weirdness to a whole new level. It's a bizarre phenomenon where two or more qubits become linked, even if they're physically separated by vast distances. Imagine two coins flipping in perfect sync, always landing on the same side, even if you flip them miles apart. That's entanglement. It's as if the two coins are communicating instantaneously, violating the laws of classical physics. In reality, entangled qubits don't communicate faster than light. Instead, they share a special connection that transcends distance. Measuring the state of one entangled qubit instantly determines the state of its partner, no matter how far apart they are. This spooky action at a distance is a powerful resource for quantum computing. It allows us to create complex quantum systems where multiple qubits work together, exponentially increasing their computational power. Section 5, Quantum Gates, Orchestrating Change. Just like classical computers use logic gates, such as AND, OR, and NOT, to manipulate bits, quantum computers use quantum gates to manipulate qubits. These gates are mathematical operations that change the state of a qubit, or a group of entangled qubits. Imagine a choreographer directing a group of dancers. Each dancer represents a qubit, and the choreographer's instructions are the quantum gates. By applying a sequence of gates, we can perform complex quantum computations. These quantum gates exploit the principles of superposition and entanglement to perform operations that are impossible for classical gates. For example, a quantum gate can put a qubit into a superposition of states, flip its state, or entangle it with another qubit. By carefully designing and combining these quantum gates, we can create quantum algorithms, which are sets of instructions for performing specific tasks. These algorithms can leverage the power of quantum mechanics to solve problems that are intractable for classical computers. Section 6, Quantum Cryptography, Unbreakable Codes. The unique properties of quantum mechanics, particularly entanglement, offer tantalizing possibilities for creating unbreakable encryption methods. This is where quantum cryptography comes in. Imagine sending a secret message written on a series of polarized photons. Any attempt to intercept and measure these photons would disturb their delicate quantum state, alerting both the sender and the receiver to the eavesdropping. This is just one example of how quantum cryptography leverages the principles of quantum mechanics to secure communications. It's like having a lock that automatically changes its combination the moment someone tries to pick it, making it virtually impenetrable. Quantum key distribution, or QKD, is a leading example of this technology. It enables two parties to share a secret key that can be used to encrypt and decrypt messages, ensuring secure communication even in the presence of eavesdroppers. Section 7. Quantum Computing in Action, from Medicine to Materials. While still in its early stages, quantum computing has the potential to revolutionize various fields, from medicine and materials science to finance and artificial intelligence. For instance, in drug discovery, quantum computing can simulate complex molecules and their interactions to design new drugs and therapies, accelerating the development of personalized medicine. In materials science, it can help design new materials with enhanced properties, such as lighter and stronger alloys for aerospace or more efficient solar cells for energy. In financial modeling, quantum computing can develop more accurate and sophisticated models for risk management, portfolio optimization, and algorithmic trading. And in artificial intelligence, it can enhance machine learning algorithms, leading to breakthroughs in image recognition, natural language processing, and autonomous systems. These are just a few examples of how quantum computing could transform our world. As the technology matures, we can expect even more groundbreaking applications to emerge. Section 8. The Future is Quantum, a Call to Explore. Quantum computing is a journey into the unknown, a leap into a realm where the familiar rules of classical physics no longer apply. It's a field brimming with challenges and opportunities, a testament to human ingenuity and our thirst for knowledge. As we venture further into this uncharted territory, one thing is certain: the future is quantum. The only question is, are you ready to be a part of it? Embrace the weirdness, explore the possibilities, and join the quantum revolution. Section 9. Share the wonder. If you found this journey into the quantum realm as fascinating as I do, then share the wonder. Let's spread the word about this revolutionary technology and inspire others to join the exploration. The more minds we have working on these complex challenges, the closer we'll get to unlocking the full potential of quantum computing and shaping a brighter future for everyone. Quantum computing is the future of processing power. Key principles: qubits, superposition, entanglement. Real-world applications are already transforming industries. Don't forget to subscribe, comment, or ask any questions you have about quantum computing. Let's keep the conversation going.